And one of them is this theorem in combinatorics called Hall's-Mariage theorem. So what does Hall's-Mariage theorem say? Hall's theorem says that okay. So before defining the theorem, let me define what is called a system of distinct representatives. So it is like this. So the idea of Hall was that, like, suppose you have, let's say, a set of men and women, right? I mean women, and let's say that women have preferences for men. Okay? So like each each lady is now asked to give a list of men she is willing to marry, right? And then you what you do is that you try to see whether you can find a matching which for these people, right, men and women, so that each man can get married to one of the ladies who prefer him, right? So if you can find at least one such matching, we can say that okay, all of them can get married. Right? So every lady has a preference whom she is willing to marry, others she is not going to marry, right? And men, of course, doesn't have any such preference. As far as he can get some body to marry, he is happy. So finding such matching, right, is it's called that is why it's called marriage theorem. Okay? But there is a much general statement in set theory which we are going to state here. So this is called a system of distinct representatives. So given a family of sets, let's say A1, A2, etc., AN. Okay? So A1 to AN are a family of sets. A system of distinct representatives for this family is an n-tuple, right, of elements x1 to xn, right, such that each element xi, right, is is a member of AI. Okay, so I have to pick xi's from AI, right? So I want to find representatives of each of the sets, right? So I have to pick xi's from the corresponding sets, and they must all be distinct, right? I cannot pick an element who is going to represent two different sets, right? So xi must be different from xj whenever I not equal to. So I want to pick up elements such that they represent the sets, right? And they are distinct. So for each set, I need a representative, right? Now, when is it possible to find such representatives for a set system? Okay? We will assume that all these sets are basically defined on a universal set, let's say U, where all the elements are drawn from, right? So of course they could have intersections, right? I mean A1 and A2 all have intersections. Otherwise we can clearly select. If they are non-empty, we can just pick elements one from one, right? One from each of the sets. You can find representative. But when they have intersections, this may not always be possible. So Hall's condition, right? Hall's theorem gives a condition when this is actually possible, right? And it is very, very interesting because one of the obvious conditions is also a sufficient condition. The necessary condition is, obvious necessary condition is also a sufficient condition. So what is the obvious necessary condition? That if I want to find such representatives, right, then for every union, right, of the sets, right? So if I take the union of sets, like say A1, A2, A3, right, like for some AK. If I take the union of the sets A1 to AK for some K, right, or some subset of the sets, right, take the union. If the union has less, right, so union of K sets has less than K elements in common. That can happen, right? For example, each set has, let's say, 2 elements, or something like that. And then they have many intersections, right? Like 1 and 2 are used here, 2 and 3 are used there, 3 and 4 are used there, 1 and 4 are used here, right? 2 and 4 are used somewhere else, right? In different sets. then the union of these 6 sets might have only 4 or 5 elements, right? In that case, you can definitely not find a representative for each set, right? Because the total number of elements in the universe is less than the the number of sets. You cannot find distinct representatives. So, so the necessary condition that is obvious is that for every indexing set J, right, J subset of 1 to n, union or all J in J, right, for any J subset of 1 to n, right, Aj, right, the union Aj, the cardinality of this union must be at least the number of sets that we are considering, which is cardinality of J, right? So, if this is not true, we cannot find a representative, right? Even for some arbitrary subset, right? If this is true, right? For some subset that we are choosing, right? This fails, then we cannot find a representative. So therefore, this must be true for every possible subset J of 1 to n, right? If A1 to An are the sets that we are considering, then for every subset J of 1 to n, we should have the union Aj over elements in J must have cardinality at least the number of elements in J, right? So this is the obvious necessary condition. But Hall's theorem says that if this property is true for every subset, right, then we can find a system of representatives for finite set systems. So if the set system is finite, right, that we are looking at only finite sets, then we can do this. If we are looking at infinite sets, it need not be true. So finite set systems, when every set that we are considering A1 to An are all finite sets, then we can clearly find a system of distinct representatives according to Hall's theorem. So this is what we want to prove. Okay. So now what we are going to prove this is using a version of the same theorem in terms of graphs. We will prove the graph version of the theorem, and then using that graph version, we will see that it is actually identical to this version. We can prove the same here also. Now, before proving the graph version, let me introduce a couple of other notions. Okay, so this will be useful to prove our later equivalences between several of the theorems that we were proving. So what we are going to now do is to use Menge's theorem to prove one theorem, and then use that theorem to prove Hall's theorem, right? And to just show the equivalence of these results in some sense. Okay, so what we want is the following. So given a graph G, a matching is a set of pairwise disjoint edges. Okay, so a matching in the graph is a set of pairwise disjoint edges. So for example, this set of 3 edges, the blue edges, form a matching in the graph, right? Because these edges are they don't have any intersection for any pair of them, right? So they are pairwise disjoint, and they are a subset of edges. Right? So therefore, it's a matching in the graph. Now you can also talk about some other matching. For example, this edge, right? If I pick this edge, and then of course I cannot pick this edge because they have intersection. So instead of picking that, I can pick something which does not intersect. For example, this itself, right? So this yellow edges form a matching, right? Or I can pick, for example, this and this, right? That is a matching. Or this and this is another matching, right? So we can find matchings like this, right? Or I can pick this, right? And then this. This is another matching, right? So we can find matchings like this. So a matching is just a pairwise disjoint set of pairwise disjoint edges. Now a matching of maximum cardinality is called a maximum matching. Okay. So one can prove the maximum matching in this graph is 3, right? Because every matching uses 2 vertices, so of course you cannot have more than n by 2, right? Floor of n by 2 edges in any matching. So that is immediately clear. So matching of maximum cardinality is a maximum matching in the graph. But of course, you can have graphs with much smaller number of matches, right? For example, if I take this graph, right, it has many vertices and edges, but the matching cannot have more than one edge, right? Because if I pick any one edge, right, let's say this edge, then I cannot pick anything else because everything else is going to intersect with this vertex. So this is the maximum cardinality of matching is 1 here, right? Now, so the Hall's theorem, the graph version of Hall's theorem is the following. So let G be a bipartite graph, which we call an XY bipartite graph because one side of the vertices are called X, right? That set is called X, and the other independent set is called Y. Okay. So consider an XY bipartite graph G, right? Then G has a matching from X to Y. Okay. So matching from X to Y is that matching that saturates X. Okay. What do I mean by that? That a matching where all the vertices of X have some edge incident to it in the matching, right? So some matching edge must be incident to every vertex. Then such a matching is called a matching that saturates the set X. Okay. Of course, there could be some vertices in Y which are not mapped. Okay. So such a matching is a matching which saturates X, right? On the other hand, you can also have matching which saturates Y, right? For example, like this. And then, this and this are matching edges which saturates Y, but not X because X has more vertices. And therefore, I cannot saturate X. Right? So this is possible. So a matching which saturates X, okay, is there if and only if for every subset of X, okay. So let us say S is some subset of X. For every subset S of X, the cardinality of S is less than or equal to the cardinality of the neighborhood of S. So what is the neighborhood of S? Neighborhood of S is the set of all vertices which are adjacent to the elements of, right, the vertices in S. Okay? So for example, right, neighborhood of this set, right, is basically, what is the neighborhood of this set? Let's say neighborhood of this set is the set of vertices which are neighbors to this, right, like these guys. So what we are saying is that if for every subset S of X, we can show that the cardinality of S is less than or equal to cardinality of its neighborhood, right? There are more number of neighbors, right, or at least as many neighbors as the elements of the set itself. Then you can find a matching which saturates X. Okay? So if in other words, if Y is the set of ladies and X is the set of men, right, and the edges are representing the preferences of the ladies. Okay, so every lady says that, okay, I prefer prefer these guys. So I can define a bipartite graph as follows, right? I can define a bipartite graph like this. So this is the set Y, right, with the ladies and then the men, and then each lady says that, okay, I am willing to marry these two guys, right? And this lady says I am willing to marry this guy. This lady says that I am willing to marry this guy, right? And maybe also this guy, and something like this is given, right? Then you are asked, okay, can you find a matching which saturates X, which means that can you find a matching for each of the men, right? Some lady who prefers him, if that is possible or not. So Hall's theorem says that if for every subset you can find at least that many ladies in the neighborhood, right? That many ladies preferring that subset of men, then we can find a match. Okay. Now, again, to prove this, we are going to use a slightly related concept. Of course, we can directly prove this. We can prove this without using any other theorem. But we are going to prove it using an application of Menger's theorem that we just learned. Okay, so we are going to define what is called a vertex cover. Okay, so maybe you should stop and think about the previous definition, because we have defined many things today. Just think for a few minutes and then come back to this. Okay. So a vertex cover is a subset of vertices, right? A subset of V, such that every edge, right, in the graph is incident to some vertex of S. So it's actually a vertex cover of the edges. Okay? So vertex cover is basically you cover all the edges of the graph by the vertices, which means that if you remove this subset of vertices, then all the edges in the graph must be destroyed. So you will get an empty graph. Right? You will get vertices maybe, right? Other vertices will be there, but there won't be any edge. So every edge must be incident to one of these vertices. So such a subset is called a vertex cover. Okay. So here is a graph and its vertex cover. So what is this? So this is our graph G, and we have this cover, right? So this vertex, right? This vertex, this vertex, this vertex, and this vertex. They cover all the edges, because if I take any edge, look at any of the blue, right? Edges, all the edges are blue, is incident to at least one of these vertices, right? Right, this is incident to both edges, that is okay. This is incident to both edges, okay. But it is every edge is incident to at least one of these. So then it's such a subset of vertices is called a cover, right? Vertex cover. Here is another example. There is a bipartite graph, right? And of course, one side, one of the independent sets in the bipartition is going to give you a cover, because every edge must be going from this side to that side, right? So we can easily find a cover in this case, but it need not be always possible to find the smallest cover easily like this, but you can always find a cover immediately like this, right? You just pick one such subset of vertices. Now such subsets of vertices are called vertex covers. Now our question is that can you relate between the covers, right, of a bipartite graph and the matchings, right? So can you find a relation between the coverings and matchings? Okay. So can you think of some relation between the coverings and matchings? Okay. So think about this. So the theorem by a mathematician called Konigs says the following, right? The maximum size of a matching in the graph, in a bipartite graph, of course, is equal to the minimum cardinality of a vertex cover. Okay. So the maximum size of a matching in a bipartite graph is actually equal to the minimum cardinality of a vertex cover. So the selection of vertices which will cover all the edges, right, in a bipartite graph will give you the cardinality of the largest matching that you can find. Now you can see how this relates, right, with the cover and matching, and how it relates to Hall's theorem somehow, right? So the maximum size of a matching in a bipartite graph is equal to the minimum cardinality of vertex cover. So for example, if you look at this bipartite graph, right, can you find a cover of the edges, right, of the minimum cardinality, and show that it is actually the largest matching that you can find out, right? For example, I say that this one and this one, right? This one and this one, right? This defines a cover of all the edges, because all the edges are incident to these four vertices. So therefore, you will not be able to find a matching of size larger than this. Okay. Now, similarly, you can always find a matching of this size. So that is why it's an interesting. For example, I can just pick this guy, right? Then this one, right? This one and this one. This is a matching of size 4, but you will not be able to find a larger matching. Okay. Now, one direction you can immediately see and we have to prove the other direction also. Okay. So Konigs theorem we are going to prove using Menger's theorem. So how are you going to prove? Of course, you can prove Konigs theorem without using Menger's theorem, but let us try to apply Menger's theorem to prove that the maximum size of matching is actually equal to the minimum cardinality of vertex. So how do you connect the Menger's theorem to this? Okay, so that is the question. So you think about this for a minute, right? Then we will prove it. So to prove Konigs theorem, I am going to introduce two new vertices. Okay, so I am going to introduce a vertex here, call it U, which is adjacent to all the vertices of the set on this side, which is called X. Okay. Then I am going to make another vertex which I call V, and this V is adjacent to all the vertices of Y. Okay. So I make a new graph from the bipartite graph, right, by adding these new vertices U and V. Now U and V are not adjacent in the graph. Then what the Menger's theorem says is that the minimum cardinality separating set from U to V, right? Minimum cardinality separating set from U to V is precisely the number of vertex disjoint U to V paths in this graph. Okay. Now, suppose you can find a separating set from U to V, right? Suppose you find a separating set, UV separating set, right? All the paths from U to V must be destroyed by deleting these vertices. Okay. Suppose you find such a separating set. Now, this UV separating set must delete all the edges, right? All the edges of this blue graph, right? Because if it does not delete all the edges of this blue graph, there must be some blue edge, which means that I should be able to go from U to that vertex. Using the blue edge, go to some vertex of Y, and then from that vertex Y directly to V, right? That path must exist if the separating set does not cover all this, right? So therefore, any UV separating set, right? Any minimum UV separating set must necessarily be a cover of the bipartite graph, right? So a minimum UV separating set corresponds to a maximum maximum number of disjoint UV paths, right? By Menger's theorem, but which corresponds to maximum matching in the bipartite graph, right? Because why maximum number of disjoint UV paths must use necessarily distinct edges from this the bipartite graph, right? The blue edges. Any such path from U to V must use edges of the bipartite graph, and they must all be disjoint, right? They must form a matching because they must be all they are all internally disjoint, right? So therefore all such edges will give a matching in the bipartite graph, right? These paths will define the matching, and that is a maximum cardinality matching, right? Because if there is one more edge which is there is a matching edge which was not covered, that will give a new path, right? Because this vertex and this vertex, these edges are present because we did not use any of these vertices, right? So therefore, once I selected the separating set, that must give me exactly the the cardinality of the maximum matching in the bipartite. So therefore, a minimum UV separating set corresponds to maximum number of disjoint UV paths, which corresponds to maximum matching in the bipartite. But the minimum separating set also corresponds to minimum cardinality vertex cover, because if all the edges are not covered, there will be some remaining edge, right? Blue edge. That blue edge is going to create one more path, right? So therefore that edge is not covered, means that that is going to give one more path, which means that we did not select all the separating vertices, right? So therefore this corresponds to vertex cover in the bipartite graph. So therefore we get a connection between the vertex cover and the size of the maximum matching. So the minimum vertex cover is actually equal to the maximum bipartite matching. Right? Because any separating set must use vertices of x and y only, right? In the blue part, right? Because u and v cannot be deleted in the separating set. Okay. So we proved Menger's theorem. And then using Menger's theorem, we just proved the Konigs theorem, right? Now, Konigs theorem gives a connection between the minimum vertex covers and the maximum matchings. Now, using the Konigs theorem, we will prove Hall's theorem, right? Hall's theorem is the statement that if this condition, right, the Hall's matching condition is true, then there is such a matching which saturates one of the sides. So we are going to prove that. We are going to now prove Hall's theorem by using Konigs theorem. So how are we going to do that? So suppose that the neighborhood of a set S is has more, at least that many elements as in S for every subset of X. Okay, so XY bipartite graph we are considering, and we are saying that for this XY bipartite graph, every subset of X has at least that many neighbors in Y, right? Okay. Now let us start with a vertex cover of the graph G. We call it C. Okay, so C is a vertex cover of the graph G. Now let me define Cx, subscript X as the intersection X, right? The vertices in the cover which appear on the side X, right? And there are some vertices which appear on the side Y also, right? So Cy is the set Cy, C intersection Y, and Cx is the set C intersection X. Now cardinality of C, right, the cardinality of the cover is basically the cardinality of the vertices in X plus the cardinality of vertices in Y, right? The cover vertices in X plus the cover vertices in Y. Now this is, right, is at least, of course, the cover vertices in X plus the cardinality of the neighbors of X minus C of X, right? Because if you look at X minus C of X, X minus C of X, right? So X minus C of X is a subset of vertices, right, in X. Now the edges, right? These guys has, let's say that it has some neighbors in Y, right? So X minus C of X has some neighbors in Y. Now all these neighbors must be covered by, so because the edges going from this X minus C of X to Y must all be covered by some vertices, right? Which means that those vertices, right, which go from this, right, these neighbors must be picked up by the vertices in Cy, right? Because vertices in Cx cannot pick up the edges which are incident to these elements, right? Because the vertices in Cx are only, the edges from this are only going to Y. So the edges which are starting from this vertex will not be picked up by this vertices, right? So therefore Cy must be at least, right, all the elements in the neighborhood of X minus Cx. Right? They must be covered by Cy. Now, but by Hall's condition, the neighborhood of X minus Cx, the cardinality is greater than or equal to the cardinality of X minus Cx. right? Because every subset, x minus x is a subset of x, its neighborhood has strictly larger cardinality. So therefore, this is, not strictly, it has at least that many cardinality, right? So this is greater than or equal to cardinality of Cx plus cardinality of x minus Cx. But what is cardinality of Cx plus cardinality of x minus Cx? That is cardinality of x itself. So what we proved is, in fact, cardinality of C is greater than or equal to cardinality of x, right? Which means that the covering, right, has at least these many vertices in the graph, right? Now, from this, Hall's theorem follows, right? Because if the covering has, these many vertices, then, like we started with any arbitrary cover, right? So therefore, in particular, it could have been a minimum cover, right? So if I started with a minimum matrix cover has at least these many vertices. But what we proved earlier that by Konigs theorem, the cardinality of minimum matrix cover is actually the cardinality of the maximum matching. Now in the bipartite graph, if a maximum matching has these many edges, they must use all the vertices of x, right? Because every edge must go from x to y. And every matching is an independent edge. So therefore, it must use all the vertices of x. So that proves the graph version of Hall's theorem, right? That there is a bipartite matching which saturates the side x if for every subset of x, its neighborhood has at least as many elements as in the subset. So we applied Menger's theorem to prove Konigs theorem for the matching in bipartite graphs, right? Which relates the vertex cover and matchings. And then we use the Konigs theorem to prove Hall's theorem, because Hall's theorem's condition gives a direct way to look at the vertex cover, and that translates to bipartite matching in the Konigs theorem, right? So therefore, we get a bipartite matching theorem of Hall's using our Menger's theorem. Of course, you can take it as an exercise to prove Hall's theorem without using either of these theorems or using directly Menger's theorem, right? All this can be done. So, but we just give a proof using Menger's theorem to Konigs theorem and Konigs theorem to Hall's theorem. Right? Now, maybe you can use Hall's theorem to prove Konigs theorem or Menger's theorem. These can be good exercises to work out. Now, using the bipartite version, right, or the graph version of Hall's theorem, we are going to prove the set theory version of Hall's theorem. So, the general Hall's theorem from the graph version. How do you prove this? So, let A1 to AN be a family of finite sets, right? This is our theorem statement. Such that for every sub collection of these families, their union has at least cardinality of the union is at least the number of sets involved in the union, right? So for every j subset of n, right, union overall j in j, aj is at least cardinality of j, right? Now, suppose this is true, right, for every such subset, then we construct a bipartite graph as follows, okay? We can of course construct a bipartite graph from the given family always. So given a family A1 to AN, we form a bipartite graph by taking the elements of AIs and taking the union, right? And this union as the set Y. And then each of these sets as the elements of this set X, okay? So one side you just write down the sets in the family A1 to AN, as the vertices, and on the other side, you take the universe from which all these elements are drawn, right? The union over all AI as the elements of Y. Okay? So these are the vertices. Now, two parts, right? X and Y. If there is an edge from AI to an element Y, if and only if Y is an element of AI. Okay. So this is basically kind of an incidence graph, right? The bipartite graph, which says that A3, right, is basically connected to all its elements, right, in the universe. A4 is connected to all its elements. AN is connected to all its elements, right? So this is the incidence graph, which is the bipartite. Now, what is a system of distinct representatives? Well, a system of distinct representatives is precisely a choice of elements here, right? Such that each element belongs to precisely, it belongs to a corresponding set, right? So what is that translate to? That translates to basically a matching, right, in the bipartite graph, because each element must have a corresponding, each set must have a corresponding element which it belongs to, and that will only happen if there is an edge in this graph, right, which can be picked as part of a matching edge, right? And therefore, if there is a matching which saturates A1 to AN, right, which saturates the side X, then of course we know that you have a system of distinct representatives, right? Because this matching will give you precisely the representatives of the elements matched in the set side Y, right? So all you have to just do is to see whether the matching condition holds. But the matching condition is precisely the neighborhood of any subset must have at least that many here, right? But that is precisely what we are saying here, right? What is the neighborhood of a set? It is basically the union of all the elements in that sets. But the condition is true, right, according to our assumption, and therefore the matching exists. So there is a matching which saturates the side X, or in other words, there is a matching which saturates A1 to AN, which says that there is a system of distinct representatives, right? And that is true if and only if this condition is true, right? So therefore, we get the general Hall's theorem, right, or system of distinct representatives from the bipartite version of Hall's theorem. So we proved several theorems today, right? Menger's theorem, then Konigs theorem, and then Hall's theorem, both the graph version and the set theory version. Okay. Now, we just finished this lecture with a few observations, and what I want to point out is that these three theorems, of course, we saw that they are kind of equivalent, right? One can be obtained from the other. I did not prove all the directions, but you can take it as a homework. But they are also equivalent to many other theorems. Okay? So I am going to show the equivalence of 7 major theorems, 7 or 6, I don't know, in combinatorics, which are all equivalent to Menger's theorem, for example. Right? So one of them is Menger's theorem, right? So Menger's theorem gives a relation between the cuts and connectivity, right? The separating sets and the number of disjoint paths, right? Then another theorem which we did not prove is Koenig-Egerberry theorem, right? Which says that the time rank of a 0-1 matrix is equal to the minimum number of lines whose removal makes the matrix a 0 matrix. So what is the time rank? Time rank is the the number of non-zero entries that you need to pick up, right? In the 0-1 matrix, number of ones that you need to pick up, such that no two of them are in the same row or column, right? So the such ones, how many maximum number of such ones that you can pick up, that is the time rank, right? Now the minimum number of lines, right? So line is basically a row or column, right? So in a matrix, any row or a column is called a line, right? Now the minimum number of lines that you need to remove to make, the matrix, the remaining matrix is just a zero matrix. That is called the that is the minimum number of such lines, and that number of such lines is called the term is also equal to the term rank of the 0 1 matrix. That is the Koenig-Eggervary theorem. Okay. This has a graph version. You can think about what could be the graph version. Then our Konig's theorem, that the maximum matching in bipartite graph equals the minimum matrix cover. Okay, so this is the Konig's theorem. Then the Hall's theorem, which we just proved on the existence of a system of distinct representatives. Then you have Dilworth's theorem. Okay, Dilworth's theorem on partially ordered sets. So if so, what does this theorem say? It says that if the largest anti-chain in a poset has size k, then the poset can be decomposed into k disjoint chains. Okay. So if you remember, chains are the totally ordered subsets, right? So you can basically partition the poset into k disjoint chains if k is the largest number of anti-chain. Okay. So that is the Dilworth's theorem. Then there is Max-Flow-Minkert theorem. So Max-Flow-Minkert theorem is a theorem in the flow theory. Flow theory is basically a study about movements of transportation of networks. You have directed graphs where you have capacities for each of the paths, right? Each path can take at most some amount of information, data, or load, right? So it could be like network, data network, or it could be transportation network, communication network, etc., where you have specific directions and bandwidths, right, which are the capacities. Then of course the flow is basically the movement of information or data or objects, which cannot be more than the capacity, right? So then you can define this network as a directed graph with associated weights of the edges, which are the capacities. And then the Max-Flow-Minkert theorem says that if you have a source where everything is static, right? It's basically a factory which produces things like S, and there is a terminal which is the outlet, maybe, right? So you want to transport things from the source to the terminal, and the numbers given here are the capacities of the lines, right? The transportation, right? There is a bridge here which cannot carry more than 2 tons. There is a bridge here which cannot carry more than 10 tons, right? This will not permit trucks of size larger than 9 to go through this, right? Things like that, right? So these are the capacities, and then the flow is basically how much of the loads can be transported at the same time, right? Something like that. I am not being precise here. One can make it precise, and then you can talk about the maximum amount of flow from S to T that can happen, and this can be equal to, this will be equal to the minimum cut which separates S to T and the sum of the capacities, right? So the sum of the capacities in a minimum cut, right, is basically equal to the maximum flow that can happen. So flow has some additional things, like for example, whatever enters a node must also leave the node except for the starting and ending node, right? So it's basically whatever going in, right? So we are going to associate some numbers here to define the flow, right? So some value is going from here, then that must also go out of this, right? For example, if this guy only allows to go 7, right, from here to here, then I cannot send 10 here, because if 10 comes here, the 10 must go also out. So the incoming and outgoing must be balanced, right, in a flow. So whatever, all these conditions there, we can show that the maximum flow is precisely equal to the minimum cut of the capacities. So this is also identical to these theorems that we had discussed before, Menger's theorem, etc. And then there is also another interesting theorem, which is the Birkhoff-von Neumann theorem, which says that any doubly stochastic matrix can be written as a convex combination of permutation matrices. Okay. So doubly stochastic means that the sum of the rows, and so it has non-negative real values, and the sum of the rows and columns are all 1. So then it's doubly stochastic. Okay, so this matrix can be written as a convex combination of permutation matrices. So all these theorems are kind of equivalent. So this is what we wanted to say for today. Okay, so I will end the lecture, and we will stop the graph theory lectures for the time being, and we will look at other topics like probabilistic method and maybe species of combinatorial structures in the coming classes. Okay, so we will see you in the next class.